Hey folks, how's it going? So we're looking at question number 8 again because the last time I tried to solve it, I did something wrong, and I apologize for that. What we did last time, if you remember, we came up with this equation, right? A squared minus 2 equals a, and we said that any value of a that satisfies this is going to be the correct answer, right? So we saw that a equals to 2 satisfies it. You might have since noticed that a equal to -1 also satisfies it. But that's not the problematic part. The thing is, this is going to make f of x continuous, but only around the point 0, right? And I actually thought that that's the only point that's going to give us a problem, but that's not true. The problem lies with this part, you know? The problem here is that for any value of x, which is of this format, n times pi, right? So let's say pi or 2 pi, 3 pi, stuff like that. What happens is tan of x actually goes to 0, right? And the tan of x, we have that in the denominator in this part, right? So that actually might give us a problem. So I'm going to try to see what happens at these numbers, right, when x is a multiple of pi. And, it might turn out that no value of a is going to make it continuous. Okay, so I'm going to try to take a look at that now, right? One sec. Okay, so let's take a look at this part, right? A times x over tan of x. X is bigger than 0, that's fine, we don't mind, right? So let's take a look at what happens when x goes to pi, right? Ax over tan x, right? We want to see this limit exists, right? So actually first, let's take a look at x going to pi from the left side, right? So a little bit less than pi. That's going to give you a times basically pi, right? Over, I can shift the limit sign underneath, pi negative tan of x, right? And if you notice, for x at pi, right, the curve of the tan of x, it actually looks something like this. What does it look like? Like this. This is the asymptote at pi over 2. Then it goes like this, right? And this is the value of pi, okay, on the x-axis. So you see, when we're a little bit less than pi, tan x is going to be some number close to 0, but it's still going to be a negative number. Does that kind of make sense? Right? Because we're right here. That looks like a big distance, but we're going to be very close to 0, but not quite 0, right? We're still in the fourth quadrant. Okay, so what's going to happen in this formula is that you're dividing by 0, or sorry, dividing by a number very close to 0, but it's a negative number, right? And a is a constant, right? Pi is a constant. So it doesn't really matter, what a is, because dividing by something very close to 0 is going to make it go to infinity, right? Negative infinity, actually. Right, and I'm going to keep this figure handy for the next part. Basically, if you look at the limit from the positive direction, it's ax over tan x, right? And without trying to simplify it, it's going to be very similar to this case. The only difference is that now we're a little bit beyond pi, right? So instead of being here, right? Now maybe we're here, right? So now we're dividing a times x by a number very close to 0, but it's a positive number, right? And that's going to be plus infinity. Okay, so you see the limit at x goes to pi does not exist for a times x divided by tan x, right? Which means it's not continuous at these values of x for any multiple of pi. So the thing is, it won't matter what value of a we come up with, right? It could make f of x continuous on 0, but it's not going to be able to make f of x continuous for all real numbers, right? Because pi is a real number. Okay, I hope that makes sense. The final answer is that there is no value of a, which is going to make f of x continuous for all real numbers. And once again, I apologize for doing it wrong last time. All right.